Look around you. The world feels solid, real. You can feel the ground beneath your feet, the weight of your phone in your hand. We trust our senses. We live in a three-dimensional world. But what if I told you that this, all of this, might be a projection, a magnificent and incredibly detailed illusion, like a shadow on a cave wall? What if the key to unlocking this profound mystery lies in the most destructive and enigmatic places in the universe? Black holes. This isn't science fiction. This is the holographic principle, and it's an idea that suggests reality as we know it might be a hologram, a theoretical framework that's challenging everything we thought we knew about the cosmos. Our story begins with a crisis in physics, a battle between two titanic theories: Einstein's general relativity, which describes the gravity and warping of space around black holes, and quantum mechanics, the rules of the very small. For decades, they've been at odds, and the battlefield was the edge of a black hole, the event horizon. According to Einstein, if something falls into a black hole, it's gone forever, lost to the universe. But in the 1970s, Stephen Hawking made a stunning discovery. He realized that black holes aren't completely black. They leak. They emit a faint glow of radiation, now called Hawking radiation. And here's the problem. Hawking showed that this radiation is random. It contains no information about what fell in. It's just thermal static. So if a black hole eventually evaporates and disappears, all the information about the stars, planets, and atoms it ever consumed would vanish with it. But quantum mechanics has a fundamental, unbreakable law. Information can never be truly destroyed. You can burn a book, but if you could somehow collect every wisp of smoke, every speck of ash, and trace every photon of light, you could, in theory, reconstruct it. The information is preserved, just scrambled. So physicists were left with a terrifying question. When a black hole dies, does it break the universe? This is the black hole information paradox. In the 1990s, a radical solution emerged, pioneered by physicists Gerard and Leonard Susskind. What if the information isn't lost inside the black hole? What if it never actually falls in? The idea is this: all the information about everything that falls into a black hole is not stored in its mysterious interior, but is encoded on its two-dimensional surface, the event horizon. Think of it like this. The event horizon is like the memory chip of the black hole. A tiny, fundamental bit of space on this surface stores a piece of information, like a pixel. The total information of the three-dimensional interior, every atom, every particle, is perfectly painted on this two-dimensional canvas. We're all familiar with holograms. On a credit card sticker, it's a flat 2D surface, but it creates a stunning 3D image. If you break the sticker in half, you don't get half the image, you get a fuzzier version of the whole image. Every part contains the information of the whole. The holographic principle applies this same logic to the universe. A black hole becomes the ultimate hologram. The 3D space inside it is a projection, a decoding of the information stored on its two-dimensional boundary. This elegant solution preserves the fundamental law that information cannot be destroyed. But it's important to understand this is a theoretical proposal, not yet proven fact. It's a mathematical framework that resolves the paradox on paper, but we still lack direct experimental evidence. Now, take this logic and expand it. If it works for a black hole, could it work for everything? Could our entire universe, with its hundreds of billions of galaxies, its swirling nebulae, and us sitting here on this pale blue dot, could it all be a holographic projection? Physicist Juan Maldacena provided groundbreaking mathematical models in the late 1990s that demonstrated how this might work. His equations showed a precise mathematical equivalence between certain types of universes and their lower dimensional boundaries. In this theoretical view, the three-dimensional universe we inhabit could be a projection from a two-dimensional surface that exists at the very boundary of our cosmic horizon. We wouldn't be able to tell the difference because the projection would be perfect. It's not that reality isn't real, it's that its true description might be written in two dimensions on the farthest reaches of space and time. And if this framework is correct, it reveals something profound about the nature of information in the cosmos. There's a fundamental limit to how much information any region of space can contain, not based on its volume, but on the area of its boundary. This is the holographic bound. It's not that the universe is literally pixelated like a computer screen. Rather, there's a maximum information density determined by the Planck scale, the smallest meaningful length in physics, about 10 to the minus 35 meters. The holographic principle tells us that the information content of any region is fundamentally bounded by its surface area, not its volume. So what does all this mean for us? If this theoretical framework is correct, it means that the solidity of the chair you're sitting on, the vastness of the ocean, the depth of the night sky, it might all be the result of a cosmic projection of information. We could be living inside the most complex hologram imaginable. The holographic principle began as a way to save information from the abyss of a black hole. But in doing so, it has given physicists a completely new lens through which to explore reality itself. It suggests that the universe might not be fundamentally a collection of things in space, but a network of information. That the deepest level of reality might not be space-time and gravity, but information encoded on a distant, two-dimensional boundary. This remains one of the most exciting and controversial ideas in theoretical physics. We don't yet know if our universe truly operates this way, but the mathematics is compelling, and it's opened entirely new avenues of research into quantum gravity and the nature of space-time. The next time you look at your reflection, remember, you may be looking at a hologram projected from the edge of the universe. At the very least, you're looking at a mystery we're only beginning to understand.